The Doppler effect is pretty important in astronomy. You might really be more familiar with the Doppler effect in reference to sound. That is, the weird distortion of a sound as it travels past you. The classic example is a train whistle, and as it comes towards you, you hear the pitch of the whistle rise to a high pitch, and then as the train passes you, it starts to decrease in pitch and get lower. That's because basically the frequency or the wavelength of what the light appears to, of the sound, sorry, appears to be changing. As it comes towards you, it's getting shorter, so that's represents a higher frequency, and as it goes away from you, it's getting longer, which represents a lower frequency. In astronomy, we use this shift of spectral lines to infer motion. That is, remember we said, say, for instance, hydrogen gas produces very distinct emission lines. If we see these lines separated by the amount that we expect, however they're shifted either in one direction or another direction, that could tell us that there's some sort of relative motion between ourselves and the source of that light. For instance, here, notice that if we allow this cloud to be moving away from us, notice the bottom spectrum is going to start to shift to the right, shift to longer wavelengths. So as it's moving away, the wavelengths get longer. Likewise, if we go in the opposite direction, notice the lines shift to the left to shorter wavelengths. In this separate range, it's a little bit easier to see because the motion is more subtle. I don't know if that makes sense, but here, notice, now we have the cloud is moving away from us. Notice the bottom lines are shifting very slightly to the right. And then as we go backwards and allow that cloud to be moving towards us, notice the lines are shifted ever so slightly towards shorter wavelengths.